Okay, in this video I'm gonna talk about the section 4.9 from the textbook, which is all about antiderivatives. So I'll do a bunch of examples of basic antiderivatives, and then I'll solve a initial value problem that deals with acceleration and velocity. So first off, let's look at a couple examples. So our main technique for antidifferentiation is the reverse power rule, right? So anytime you're faced with an integral like this, or an antiderivative, whatever you want to call it, rewrite it in terms of a power function. So the cubed root of x, right, is x to the 1/3. So that's the best way to deal with this. Also, this 6, don't even kind of ignore that. You can bring that thing through the integral. So just bring that 6 out and write the cube root as x to the 1/3. So in this case, whatever my antiderivative for x to the 1/3 is, I can just multiply it by 6, and that'll be my final answer. So the rule I'm going to use here is anytime I have x to the p, the antiderivative of that is 1 over p plus 1, x to the p plus 1. Unless p is negative 1. In the case that p is negative 1, then the antiderivative is the natural log of x. So here p is 1/3, so p plus 1 would be 1/3 plus 1. So that'd be 1 over 3 plus 3 over 3, so that's 4/3. So I would have x to the 4/3, and then I would have to divide by 4/3 and tackle my plus c. So at the end of the day, I have 6 times 3/4 x to the 4/3 plus c. So the 4 and the 6 cancel a little bit, leaving me with a, let's see, a 2 in the bottom and a 3, so this would be 9/2 x to the 4/3 plus c. So that's my antiderivative right there. Okay, likewise, we have something like this. Again, anytime I have a power function in the denominator, I can bring it up to the top. So first I would write this as 3x to the negative 4 plus 2 minus 3x to the negative 2 dx. And so in this case, right, kind of ignore the 3. Here the p-value is negative 4, so I'd add 1, and be careful, adding 1 there would be negative 3, and then I have to divide by negative 3. The antiderivative of 2 would be 2x. Here I would have 3, add 1 would be negative 1, and then I have to divide by negative 1 plus c. So here I get negative x to the negative 3 plus 2x plus 3x to the negative 1 plus c. And so my answer would be negative 1 over x cubed plus 2x plus 3 over x plus c. So that is my antiderivative right there. All right, so those are just 2 quick examples. Let's get a little bit more complicated. So say I have the integral of a product of 2 functions. Now again, the integral of a product is not the product of the integrals. So first I have to simplify the integrand by foiling this thing out. So I would get 12x minus 3x squared plus 4 minus x dx. And so here you see we just have a polynomial, and we can do the integrals one at a time. Okay, furthermore, I can actually simplify this a little bit. This would be 11x minus 3x squared plus 4. So I've combined the 12x and the negative x. So here, to keep the 11 by itself, add 1 to the exponent and divide by that number. So here it's x to the 1, so I'm going to add 1, divide by 2. All right, so add 1 to get 2 in the exponent and then divide by it. Here I would have to, that would be x cubed, right? Divide by 3, and then here the antiderivative of 4 is 4x, and then my plus c. Simplifying a little bit, we get 11 over 2 x squared minus x cubed plus 4x plus c. Okay, so here we have an antiderivative of a quotient, and my independent variable right now is t, not x. It doesn't really matter. As long as this says dt, then we're fine. So if I have the integral of a quotient of 2 functions, I cannot do the quotient of the integrals, right? I have to somehow simplify this integrand. So if I have the difference of 2 things over a single denominator, then they have a common denominator, and I can split the 2 things up into 2 different fractions, like so. So when I have 12t to the 8th over t to the t cubed, I can subtract the exponents and get 12t to the 5th. Here I'll bring the t cubed up to get t to the negative 2. Antiderivative, I would do 12, and then this would be t to the 6th, and then I have to divide by 6. Here I would have to add 1, which would be negative 1, and divide by negative 1. And so I get 2t to the 6th plus t to the negative 1 plus c. So divide by, let's see, this would be 1 over t. So I get that, plus c. That's my answer. Okay, so all 4 of those problems use the power rule, the inverse power rule, or the reverse power rule, whatever. Here's a couple transcendental functions which are a little bit more difficult. So 1 over 2 to the x. So again, you might think 1 over 2 to the x is the same as 1/2 times 1 over x. So again, don't let that 1/2 bother you. You can bring that 1/2 out. And then I'm doing the antiderivative of 1 over x, which we all know is ln of x, right, plus c. So be careful there. Antiderivative of ln, the antiderivative of 1 over x is ln because the derivative of ln is 1 over x. Now, this rule was kind of strange, right? So here's 2 exponential functions. Remember the rule that the antiderivative of b to the x is 1 over ln of b times b to the x. So I'm going to try to use this rule, plus c. So I'm going to try to use this rule. I'm first going to split the integral up, the 2 different integrals, just to focus on each one separately. Right, notice how I can write e to the 2x. I can write that as e squared to the x. And this one, what is e to the x plus 2? That's the same as e to the x times e squared dx. So here, I can use this rule right here with b being e squared. So I'll use the rule. That would be 1 over e to the ln of e squared. E squared to the x. Plus, now look, this e to e squared is a constant, so I can bring that through the integral. Right. Now what's the antiderivative of e to the x? Well, that is e to the x. So here, also, what is ln of e squared? That's just 1/2, because the ln and e cancel. And here I get 1/2 e to the 2x plus e to the e squared, e to the x plus c. Simplifying a little bit, we can rewrite this again as e to the x plus 2. So there's my antiderivative. Now, finally, where does antidifferentiation come into play? Well, this is number 6 from worksheet 4.9. It says, suppose an object is traveling in a straight line, and say its acceleration is a function of time, and it is given by this function, 0.2 times t. So it's a linear function in t. This is an initial value problem because I have the velocity function, but I also have what's called the initial velocity. And this is the initial position, or initial displacement. So s, the function s, is the displacement or the position, and v is the velocity. So the question asks, what is the unique the position function? How can I determine where this object is going to be at any time t? So first we realize that, okay, a of t, the acceleration, that is the rate of change of the velocity. Okay, so I can update this equation, a of t equals 0.02 t, to be v prime of t is equal to 0.2 t. Now again, how do I get rid of the derivative? Well, I would anti-differentiate both sides of this function with respect to t. The antiderivative of velocity, of v prime would just be the velocity. The antiderivative here will be 0.2 times 1/2 t squared plus c. So v of t is equal to 0.1 t squared plus c. Now I can use the initial velocity to solve for c. So I'll do that here. V of 0 is equal to 0.1 times 0 squared plus c. V of 0 was given to be -3, so that is equal to c because this thing will go to 0. So my velocity function is 0.1 t squared minus 3. Now notice that this whole thing hinged on this fact right here, right? That the acceleration is just the derivative of velocity. Now I want to solve for s. So I'll do that in, let's see, I'll use the orange marker to solve for s. V of t is exactly the derivative of position. So I can take this equation and write s prime of t is equal to 0.1 t squared minus 3. And now again, integrate both sides, because how do I get rid of the derivative? Well, I find the antiderivative. So I'm going to integrate both sides of this equation with respect to t. And so I get s of t is equal to, the antiderivative here would be 0.1 over 3 t cubed minus 3t, plus again another constant of integration. Plug in the initial position in here. So I would get 0.1 over 3 times 0 cubed minus 3 times 0 plus c, and the initial position was 1. So this goes away, so c is equal to 1, which means my position function is exactly 0.1 divided by 3, t cubed minus 3t plus 1. So that would be my position. So essentially, if I have acceleration, I can integrate once to get the velocity. If I have velocity, I can integrate again to get the position. Use my initial points for each one to get the value of c.